Alright, so let's go ahead and get the setup rolling. Lattice grid, right? So something interesting to note right away is that if we think of this as a series of points on squares, so we actually have 1, 2, 3, 4, 5, 6, 7, 8, 9 in a 2x2 grid. So if we want to do some sort of implementation where the arrow is moving from point to point, then we're going to need to increase the size of the grid by 1. So in order to implement a 2x2, we need a 3x3. In order to do a 1x1, you actually need a 2x2. So we use that as a base case. I'm thinking of maintaining like a global thing that we operate on. So something like oops. So I'm going to make a 1x1 lattice to start with. So actually this would be it would be a 2x2. So top left, top right, bottom left, bottom right. So we start from 0, 0. You think of this like we wanted to implement a way to like keep track of where we are. This might be one way to do it, but I realized that it may not actually help us to actually store anything in the matrix. We just need a representation for it. Because ultimately what we're going to be doing is bounds checking and then recursing across each point that we come across. So like once the recursion finishes, once we get to a certain indices, we're going to return 1 because that would count as one path. So every time the recursion resolves, we would return 1. And this way we could actually iterate over every possible movement combination. So as an example of this, we want a function like traverse lattice. So in a 1x1 case, this would actually be 2x2, right? So it would start from 0, 0. And in this case, if I is exactly equal to 1 and j exactly equal to 1, then we want to return 1. Right? So that's like our terminal case for a 2x2, because that would be the bottom right corner. So if we start from 0, 0, right, we want to return traverse lattice of, so think of it like row column, right? IJ. So if we plug in I and we want to move right, that's going to be column -1. And we're going to also want to return moving down 1 So in this case, if we start from 0, 0, it errors out. Interesting. So what happened here? Infinite recursion. So we're not properly terminating. So, yeah. All right, so we actually have to handle the other cases too. So if we're on the rightmost column, we can only move down. If I is equal to 1, we can only move right. Otherwise, we return the sum of them both. Uh-oh. Infinite recursion again. What's going on here? We want to slow this down a little bit. Oh, it's going to -1. Whoops. I meant to do plus. Silly me. Two. Okay. I like that so far. Let's increase it to a 3 by 3. Oh, yeah. So we have to fix our terminal cases here. So anytime we make the size bigger, so far so good, and it counted correctly. So we actually don't even need a real data structure for this one. So U-sleep comes from Unistandard as well. So that's microseconds, right? So I think 500,000 is half a second. So let's do a 4x4. It's computing every possible path that we can take. I like pathfinding stuff. It's pretty fun. $20. Okay. I feel pretty good about this solution. Oh, even with recursion, it's taking a while to run. Whoa. This one's taking a while. Fuck. I should have printed the stuff out just to see where stuff is at. I kind of want to do that. That'll be fun for the video. Oh, wow. It's moving so fast we can't see where anything's at, nor do we want to necessarily. If we wanted to keep track of like how many paths we've found so far, Um, and this might actually be too big of a number now that I think about it. Everything's been unsigned long int so far. Whoa. Oh, it's just printing the 1 on its own? Huh. Oh, I guess because of the recursive nature of this whole thing. Um, really, what we would want to do is like this. So maybe we don't even want to print the 1s, because it's always going to be that. I guess there will be cases where it's genuinely 1. So that's fine. Printing everything out is going to make it take so much longer to run, though. So as the numbers go up, we like the way that recursion kind of works is the last case ended up being fully computed first, so that's what gets printed out first. So everything else is going to get printed out afterwards. So 0, 0 is going to be the last thing that gets printed out. And actually, we would want to track how long this thing runs, too. All right, so we're going to use libchrono. Millisecond. This is an interesting line. Huh? I actually think this is a little bit more user-friendly. All right, just to test that the time code works. That's a fast program. So for a 4x4, also very fast. What about a 10x10? Yeah, so it's accurately tracking. Here we go. One thing that's kind of occurring to me now is that we could potentially, I would think that we could split the search up somehow. Like maybe break it up into quadrants, because it computed the 10x10 case pretty fast, right? So the 10x10 case is kind of like 1/4 of the search space, right? I would think it's like 4 times that maybe. But I don't believe that rule necessarily holds. So in essence, this is a brute force computation, but there has to be optimization techniques in order to make this faster. A lot of the other problems solve rather quickly when you do them right. So there has to be something about this. It would be convenient to be able to take the 11 by 11 or the 10 by 10 and simply multiply that number by 4. But I don't believe this correctly accounts for all the possibilities. I think there's a lot of edge cases that would be missing if we were to try to input that number. It's probably not even worth it. This would be very upsetting to get the incorrect value at this point. We have no idea where in the process we are. And BTOP is probably going crazy right now. There's our program running. Keep track of its time and memory. It looks like it's been running for almost 5 minutes now. It's taken up most of the CPU. Oh lordy. I'm gonna pause recording and pick back up when it terminates. I just realized this might be a factorial problem. Now, obviously 1 factorial is not 2, right? But for a 2 by 2 grid, there are 6 roots, and 3 factorial is 6. So similarly with a 1 by 1 grid, 2 factorial is 2, right? So let's examine this for the next case up. So this is for a 3 by 3, right? Which would be 4 factorial. 4 times 3 times 2 times 1. 20. That's not correct. Okay, so that's not a factorial problem, right? 4 times 3 is 12. 12 times 2 is 24. So our idea for the factorial doesn't work. We have not yet let the program run long enough. Now, one of the things here too is that there's a lot of recomputation occurring, possibly, right? There's a lot of paths that we already travel, and we can essentially label, or rather store, what the computations were at the time of us getting it. So instead of a Boolean array, let's have a vector of unsigned long ints. And we're going to call this path counts, because for any given position, and actually it's going to be a vector of vectors. In other words, a matrix. So as we're going through here and we're computing, we're going to need to reserve capacity for every So in the very beginning, we run through and we initialize our path counts vector and all of the vectors in it, so that when we're using traverse lattice, we can start to assign values to each of those locations in order to store what we've computed. So path counts of ij would equal 1. Path counts of ij would equal v. Path counts of ij would equal v. Now, what happens if we were to try to get the value at a location when we reserve it, right? Let's go to let's go to vector. Increase the capacity of the vector. After we call to reserve, insertion will not trigger. So what happens when we actually go to store something, right? Like, does it return 0? So we can actually find out. Oh, error. So I guess it doesn't like this necessarily, or does this have to be a reference? Oh, it still errored. Oh, still errored. Oh, wow, what? Is it the memory access that's a problem? Yeah, oh shit. I did something fucked up here. Maybe we're not going to do it as a vector. Maybe instead, just to keep things simple, all right. All right, this initializes path counts. Okay. So now that we have path counts, right? We definitely want to set that to 1 right away, all right? But then equals path counts of ij, right? If v exactly equal to 0 means we haven't computed it yet. V equals traverse lattice. And then we definitely store that value back, and then we return v. Similarly, something along v is that if that's true, we do that, then we return v. And then lastly, so by the very end of this, using dynamic programming, we should avoid having to recompute multiple things, because once we've stored something in the matrix, we will be able to use that value instead of having to do the recursion all over again. So now when we go to compute paths, seems pretty fast. We're just going up one at a time. Well, it's already faster. We managed to shave off that millisecond. It's not slowing down any, and it's still running incredibly fast. The power of pre-computing. Uh-oh, we have some overflow. Damn it. Unsigned long. All right. Let's just jump to it. All right, there's our number. How many such roots? This number. Fucking awesome. Goddamn. That took some real thinking, honestly. But once you implement the recursive solution, you can recognize an opportunity for dynamic programming right away. It's one of the most powerful techniques that you'll learn.